So in this, CCl4, when you go to draw a covalent molecule, remember that you're just going to go based on the formula. The formula tells you how many atoms you have. So you can't add or subtract. You're just going to use the ones that are listed. So we've got a carbon and we have the 4 chlorines. So if you look at the carbon in group 4, that tells you that it has 4 electrons, which means that it's going to form 4 covalent bonds in order to have a total of 8. Carbon always has 4 covalent bonds in order to create that 8. But the halogens, fluorine, chlorine, bromine, and iodine, they're all in group 7. So in order to be stable, they'll form a covalent bond with carbon, but they only need to have just 1 bond. They've got 7, so if they share 1 electron with carbon, that'll give them their total of 8. So the halogens are kind of like hydrogen. So they have 7, 7, 7, and 7. But that means that they're only going to need 1 bond each in order to create that stability. So you always start with the atom that needs the most bonds. So that would be the carbon. And then you just sequentially continue to add the other atoms, forming a bond by pairing up one of the carbon's electrons and the chlorine's 1 unpaired electron. So we'll put a chlorine up here, put chlorine over here, put chlorine down here, the 4th one here. So when you get finished, you can see that all the chlorines have 8. Each carbon is paired off with one of the chlorine's electrons, giving it 8 to create that stable structure. So it looks like there's a lot of dots, but they all now have their 8. So whether you're talking about chlorine or fluorine or bromine or hydrogen, if we look at the shape of this molecule, that carbon, if we have the carbon as the A, as the central atom, the B component of it is how many pairs are bonded to it. How many groups are connected to the carbon? And in this one, there's 4. So it's A, B, 4. That is the geometry of that carbon. Does carbon have any non-bonding electrons that belong only to carbon? No. All of its electrons are part of bonds. So it's always just going to be AB4. It would have no N with it, just an AB4. And it will always have a tetrahedral shape. So this one is, I did methane last time, CH4, but it doesn't matter if I have CCl4 because still carbon with 4 single bonds will always have that tetrahedral shape. With these others, when you begin to introduce multiple bonds, or if you begin to introduce non-bonding electrons, that will affect how evenly electrons are paired or bonded together in their arrangement. So with NH3, we have the nitrogen and we have 3 hydrogens. Nitrogen has 5 electrons. Each hydrogen has 1 electron. So in order to create stability, that nitrogen is going to have to make 3 bonds. So it's got 5 electrons. If it shares 3 with another atom, that will give it 8. Hydrogens, on the other hand, are only ever going to have 1 bond, kind of like chlorine. So you always start with the one that needs the most bonds. Put it down and lay its electrons down. Then you just add the other atoms to it, always adding to the atom that needs the most. But the key thing to remember here is you've got these non-bonding electrons actually take up space that has an effect on the position of those hydrogens. So they don't evenly spread themselves out and form that perfect tetrahedral. Instead, with the ABN designation, if we make nitrogen the A, how many groups are connected to it? 3. So that's AB3. But how many non-bonding pairs? 1. So that's an N. But what those non-bonding pairs do is they're actually going to push those hydrogens further away, causing the hydrogens to be somewhat lower than where the nitrogen's position is. So the nitrogen's a little elevated with the hydrogens kind of sticking down, and that gives an arrangement that they call pyramidal. They sometimes call this trigonal pyramidal because it looks like a little triangle at the bottom where it sits. Those 3 hydrogens form a little triangle. The pyramidal is fine. The more non-bonding electrons, the bigger this effect is, and water is a great example with this. So water, you have the oxygen that has 6 valence electrons. You know that it's got in group 6, so that tells you how many bonds would it need to end up having 8? 2. So you have the 2 hydrogens. So one's going to fit in each spot. Hydrogen here, hydrogen here. So you can see the oxygen has 8, each hydrogen has 2, that creates stability. But these electrons take up this amount of space, these electrons take up this amount of space, and they're going to have this push, this repulsion effect on the hydrogens. So the hydrogens that are just trying to share their electrons with the oxygen actually get kind of shoved by those non-bonding pairs. So if you look at the ABN for oxygen, the A of oxygen, how many groups are connected to oxygen? 2. And how many non-bonding pairs? There's 2. That's always going to make a molecule where the single bonds, instead of being straight across, the single bonds are going to be pushed, and that creates the bent. Because optimally, water would really, the hydrogens of the water would really like to be more like carbon dioxide. So carbon dioxide is when carbon has to form 2 double bonds, one with each oxygen, in order to create this stability. So when you look at this, you've got a double and the double. The oxygens still have their non-bonding electrons. But if we're looking at the shape, we always look at like the main one. So if we look at that carbon, we would say that this carbon, if it's the central atom, how many groups are attached to it? Just 2. So it's just got 2. It's got 2 oxygens attached to it. Say call this AB2. Does the carbon have non-bonding electrons? It never does. So therefore, there's no clouds around the carbon that need more space. That allows the double bonds of the oxygens to get as far apart from each other as possible. And as far apart as possible would be 180 degrees apart. So the oxygen on this side and this side, that's as far away as they could get. Water would really like to do that. But water's got those non-bonding electrons that creates that repulsion and causes that bent shape. But this one, because it makes a straight line in a row, oxygen, carbon, oxygen, they call this shape, because it looks like a line. So if you have a carbon with 2 double bonds, they'll always arrange themselves fully straight out and have a linear shape. So the last one up here is CH2O. Formaldehyde, one that we've drawn. So the carbon in order to form the complete set, the carbon has a single bond with each hydrogen, because that's all hydrogens can do, is just a single bond. but it has to share a double bond, let me get a different color, with the oxygen, two single bonds with the hydrogens. And so it ends up looking kind of like this. Stop. So if we make C the central atom in this one, you would say that it has how many groups connected? So a total of 3. It has 3 groups. So it has 4 bonds, but one is a double bond. So that counts as one group connected. So it really has 2 hydrogens and 1 oxygen, or 3 things connected to it. So they call that AB3. So does that carbon have any non-bonding pairs? Are there any non-bonding pairs connected to the carbon? No, there never is. Okay? But if you have a central atom and you have 3 things connected and you want to spread them out as far as possible, they will spread out just like this. Right? They'll spread out so that they are basically each 120 degrees apart. That is as far apart as they can get. This is a flat-looking molecule. It's called trigonal planar. So it really just looks like a triangle that's actually flat. So the carbon's in the middle, a hydrogen and one sticking off in one end, a hydrogen sticking off at the other, and the double bonded oxygen on the third. So those are the 5 different shapes: tetrahedral, pyramidal, bent, linear, and trigonal planar, that are common shapes. The reason we go into shapes is because the shapes help you to understand polarity. So polarity, being polar or nonpolar, is a characteristic that covalent molecules can have. But it is going to depend on what atoms are in the molecule and what the shape of the molecule is. So we said that covalent molecules are nonmetals and hydrogen. So the nonmetals, they tend to have an almost full number of electrons. In fact, if you look at your periodic table, other than the noble gases, which have the almost full shell? Which column is the closest to having a full set? Group 7, right? So that would be fluorine, chlorine, bromine, iodine next to the noble gases. They have 7. All they need is 1 more to be stable. Those atoms hold on to their electrons very tightly. When they talk about that pull, that's what electronegativity is. So electronegativity is just the pull of an atom for its electrons. The further across you go, the higher the number of electrons in the outer shell and the higher the electronegativity is. So the most electronegative atom or element on the periodic table is fluorine, because fluorine is really small and it has the first energy level's full, second energy level has 7. And so all it has to have is 1 more, and that's going to make it just like neon, and it's the strongest of all of them. As a general rule, you can look at these numbers and see, like they kind of grade electronegativity, and you can see metals have really low electronegativity. Metals don't really want to hold on to their electrons, they give them up. That's why they form positive ions so easily. So when you look at like lithium and sodium and potassium, their electronegativity is 1 or lower. But once you get into the nonmetals, see how their numbers increase. Carbon is 2.5, nitrogen is 3, oxygen is 3.5, fluorine is a scale of 4. So fluorine is the highest of all of them. So these are really the big ones. These ones that I've got outlined here, these big four, nitrogen, oxygen, fluorine, and chlorine, they all have an electronegativity of like strong to super strong. In fact, you can even think of fluorine would hold its electrons super close. In comparison, like if you look at carbon, carbon would allow them to be a little bit further out. And then if you went over to like lithium, lithium be like, here's my electron, take it. Okay, so it doesn't hold on to it very tightly. The higher the electronegativity, the more the pull of those electrons, and the greater the pull any electrons around them will have. So if you have a covalent molecule and you have nitrogen, oxygen, fluorine, or chlorine, they are going to pull their electrons close, and they're going to pull electrons that they share close. So they'll look more like the second one. So the first example is like hydrogen. So this is H2, right? Where two hydrogens, they share their electrons. They share them evenly. So you see how the pair looks like it's right in between? That's an even sharing of a covalent bond. The electrons like spend half their time with one hydrogen, half their time with the other hydrogen. They go back and forth evenly. But if you look at HCl, because chlorine is electronegative, chlorine is pulling these electrons towards it. And so when it forms a covalent bond with the hydrogen, it doesn't equally share. If you look at the pair, do you notice that the pair look like they're over by the chlorine more? So that means that the electron is going to be over or around the chlorine more than it is going to be around the hydrogen. And so this side becomes slightly negative. It doesn't make an ion, but it does make a slight difference in the electron density around the chlorine. That means that this hydrogen becomes slightly positive. They use this funny looking symbol down here. It looks like this. So it's a delta sign. A Greek delta sign. It looks almost like a figure eight that's not totally closed. That's what that symbol. That's the way I always draw it. So if you have an even sharing of covalent molecules, that makes a really uniform looking molecule. No charge difference between the atoms. They're basically all the same. So I think of it as being very neutral. This is a nonpolar molecule. Whereas if you have an electronegative atom in a molecule, it will always pull the electrons closer to it and create this slight difference. This they call polar. And so understanding the shape of the molecule can oftentimes help you to pick out and determine if a covalent molecule is positive or negative, or if it's actually a nonpolar molecule. There's the little symbols. So other examples, if you have very little electronegativity difference, so like anywhere from 0 to about 0.3, they'll share their electrons very, very close. So here, so if we look back at this, looking at this, the carbon to hydrogen covalent bond in methane. So carbon is like 2.5. Hydrogen is 2.1. So the difference is about 0.4. So there's a little more. The carbon is going to pull the electrons towards it a little bit more. But if you look at it, because it's a tetrahedral shape, that means that it's all balanced out. So its arrangement is the way the hydrogens are. They balance out each other. So they have a balanced arrangement. And if it's a balanced arrangement, it's going to create a nonpolar molecule. So tetrahedrals, if they have an even number, the same single bonded molecule to it, like CH4, like CCl4, so like carbon tetrachloride, that other one that we did, we could put chlorines here. Chlorines, on the other hand, would pull the bonds the other direction because chlorine's a 3. So if we had this, they would pull the electrons away from the carbon, but you would have one above, one down, one to the right, to the left, so they would be evenly arranged. That's a nonpolar molecule. So it evenly, they kind of like negate each other or balance each other out in the charge. Carbon, if it has 4 of the same groups attached, it's going to be nonpolar. Nitrogen, on the other hand, if you look at nitrogen, like in ammonia, that makes the pyramid. So that nitrogen is a little bit above, the hydrogens are a little bit below. Nitrogen is more electronegative, so that means those electrons are going to be pulled more this way. So you see how the top becomes more negative and then the bottom becomes more positive. They don't balance each other out like the carbon does because you've only got 3 bonds there. This side becomes negative, this side becomes positive. That's a polar molecule.
So CO2 is nonpolar?
That's right, because they're going to pull themselves opposite. So in looking back, so she was asking about CO2. So carbon and oxygen, oxygen's electronegative. Oxygen would pull the electrons this way and that way, pulling them away from the carbon. However, they pull in opposite directions, so they're going to balance each other. So carbon dioxide is a nonpolar molecule.
So kind of anything that has the
It has like an even arrangement.
yeah.
What, even if it has electronegatives, it's going to be nonpolar.
So the non-bonding, the ones that have
The non-bonding tend to be.
like the AB3 and AB2.
They tend to have more, well, not the AB2, but the AB3Ns and the AB2N2. Like, look at water. Water is extremely polar because the oxygens are going to pull the electrons, plus it's got its own electrons. That whole area around the oxygen becomes more negative. The area around the hydrogens become less. And so that forms that polar molecule. Because I could actually take a water molecule, the electrons go that way, the electrons get pulled that way. So can you see, you can almost like split, you can almost split this molecule in half and say this half doesn't have very many electrons and this half has a lot more. That creates that imbalance. But if they're on opposite sides, or if you see 4, then they're going to help to balance each other. What do you think with CH2O? Formaldehyde, this one. It's polar because of the oxygen. So that oxygen is going to pull electrons towards it. And notice there's no oxygens below. Hydrogen's not very electronegative, so the electrons will get pulled more towards this side. So that side becomes more negative, and then the opposite side becomes more positive. So this becomes a little easier if you just start making like the analogies of things that you know that are polar. And there's a couple of examples. That's the one with CO2, carbon dioxide. It's a linear molecule, so even though electrons get pulled towards the oxygens, it's still nonpolar. But water is going to cause those electrons to get pulled towards the oxygen, and it's bent, which means that all of them end up kind of collecting on this side. Down here becomes more positive. Here, do you see how they balance each other? So let's look at some of the ones that you know. So water. Water is one of the best examples of things that are polar. NH3, that nitrogen with those non-bonding electrons at the top, create that negative around the top, positive around those hydrogens. So that's ammonia. Have you ever mixed ammonia in water, like in cleaning? You can dilute it, right? So what's another thing that you dilute with water? Vinegar. So vinegar is going to be polar too. Things that have similar polarities can mix. So vinegar, sugar, so table sugar, put it in, mix it. Now salt, you know, is a ionic compound, right? Like NaCl. So it's not a covalent molecule, but salts, when you put them in water, they can interact with the slight positive and negative because salts are positive and negative ions. That's why salts can dissolve. So when you put a molecule of sodium chloride in, the sodium can interact with the oxygen part of water because it's kind of negative. Positive mixes with the slight negative. The chloride can go kind of hang out around the hydrogens because the negative chloride ion is similar to the hydrogen, which is slightly positive. So they're attracted, and that's the reason why salts can dissolve in water. So salts, they dissolve in the polar water. The rule, general rule you can always remember is that things that are polar mix with things that are polar. If they're covalent molecules and they mix with water, then the odds are they're polar.
So like oil is not polar.
Right. So oil. So the non-polar ones, grease, oil, waxes. What happens when you get like grease on your hands? You run them underwater? Nothing. Okay, it doesn't rinse off at all. You've got to do something to break that. Fuels, like even if you get fuel on your hands, really slippery, slimy, and you kind of like have to wait for it to like evaporate away, you really can't go in and wash it off. Gasoline, grease, oil, butter. Like you can take olive oil and butter, heat them up in a pan and mix them. Do they mix? No. Olive oil and butter.
Oh, yeah.
They'll mix. It's actually good to do that because olive oil like will start smoking at a lower temperature, but if you add a little butter, lard, or bacon grease, that'll actually raise that temperature so it won't smoke so bad. So you can mix those, things that are non-polar, all of those fuels. In the next chapter, we're going to talk about the hydrocarbons, things that contain nothing but carbon and hydrogen. These are great fuels. This is what methane is, propane, butane, octane. So all of your fuels and gasolines, those are all the non-polar. So is it a problem if you get water in your gas tank?
Yes.
Yes, because does it mix? No. And so it's going to settle out, and the water actually will settle down to the bottom, and then that's what ends up going into your engine. So that's always a big problem. So like I used to live in Maine, and so we used to put what they call dry gas in during the winter because it would get so cold that water vapor would crystallize in your gas tank. So you could end up with water in your gas tank if you didn't use this dry gas to help remove it on a regular basis. Non-polar things mix with non-polar. Polar things mix with polar. But if you mix the two of them, what do? They're going to separate. So like oil and vinegar, like Italian dressing, you shake it up. But once it sits, it's going to settle into that heterogeneous mixture. So oftentimes thinking about covalent molecules, just thinking about things that you know can help you figure out if it's something that's polar, something that's non-polar, just based on the general groups that we talk about. All right, so the last topic in this chapter, which really should be in chapter 5. I don't know why they put it in chapter 3. It's like they just go, let's just throw this in here. All right, it fits so much better if they would just cover it later. But in this is a way of actually being able to measure molecules. So molecules, we're going to draw them, like build them with the balls and sticks in lab today. But molecules, remember, we're talking about like 1 × 10⁻22 grams, extremely small. So you can't just pick a molecule up. But when molecules interact, they do so on that balanced equation ratio. So they interact at a molecular level. So scientists wanted some way to count, kind of like when we were talking about the masses on the periodic table. The atomic mass, we just had this general number they called an AMU, the atomic mass unit. Well, they wanted something similar, some way of being able to talk about numbers of atoms that were a more sort of reasonable counting unit. So they said, okay, if we have a mole, MOLE is the terminology that they came up with. The mole is a counting unit for a number of atoms of any substance that is equal to its mass. So if we have 12 grams of carbon, that is equal to 1 mole of carbon, because the atomic mass of carbon is 12. So if we take, and they even use like carbon 12, so that is carbon that all has exactly a mass, 6 protons and 6 neutrons, has exactly a mass of 12. So the formula mass, so what is known as the formula mass, it is just the mass of the atoms added up based on the formula. That in grams is equal to 1 mole. So if we had 1 mole of water, to figure out how many grams it is, you just add up the weights of each of the things in the molecule. So you got to add the weight of 2 hydrogens and add oxygen. So H2O, 2 hydrogens and 1 oxygen. So 2 hydrogens. Each hydrogen weighs what? Just look at your periodic table, look at your mass and round it to a whole number. So it'd be 1, right? So see where it's 1.008, we'll just round the mass to 1. So that means that the hydrogens are going to add in a mass of 2. Oxygen is 16. So that means there's 18 grams in 1 mole of water. So we can measure that out. So we can put that on a balance. We've been measuring grams in lab. You had to measure grams of milk and grams of your nuts and everything. So we can actually have a measurable amount. So scientists were excited. Okay, this works. Like we're going to use this with all of them. So here comes Avogadro. So there's this scientist, super smart guy, who said, okay, well, how many atoms is that? Like if we have 1 mole of water that weighs 18 grams, how many molecules of water is that? So people started doing all this calculating, I don't know. So they kept on calculating. They came up with this. So they're like, so we're going to need a calculator for this. So this is 602 and 21 zeros afterwards. So in 18 grams of water, which really is maybe like 3 tablespoons of water, there is that many molecules of water. That's how small the molecules are. So Avogadro did all this math. And they kept coming up with this. So he was doing calculations with water, calculations with carbon. So he was doing all these different substances, trying to figure out how dense they were, how much space they took up, how much their mass was, and then figure out, okay, well, how many could you fit in this space? That's where this number came about. So he got it named after him. So this is Avogadro's number. So 6.02 times 10 to the 23rd. So 1 mole of anything is 6.02 times 10 to the 23rd molecules. It could be pieces. It could be atoms if you were talking about like single carbon atoms. It could be molecules of water. So 1 mole of anything. So we now have like a measurable amount, and we can actually calculate how many molecules are present in a sample like that. And it's just like doing a unit conversion. So in doing the unit conversion, if we want to go from moles to grams, it's just a single unit conversion. All we need to know is how many grams in 1 mole. And you can use the periodic table for that. You don't have to memorize it. How many grams So carbon we said weighs
12.
and there's only one of them. Hydrogen, I've got 4, and we said hydrogen weighs 1. Carbon weighs 12, each hydrogen weighs 1, so that's going to give us a total mass of 16. So methane has 16 grams of methane in 1 mole. So if you know how much is in 1, you can figure out how much is in 3. And again, if you set it up so that your units cancel, you'll never multiply when you should have divided. You always start with the unit you're given. That unit's going to go on the bottom in the first step. Moles on the bottom, grams on the top, and that's going to allow the units to cancel. On the same note, you can go the other way. So if you know the number of grams, you can figure out how many moles that is. It's just a matter of where you put moles on top or moles on the bottom, but always just set it up so that it cancels. We can use this same number, 100 grams times the line. The unit you start with will always go on the bottom in the first one. So grams on the bottom. And the unit we want to get is moles, 1 and 16. Same molecule, so we can use that number we figured out. Grams and grams will cancel. All right.
So you can have a decimal for a mole.
So in this, if you were doing a calculation, in all honesty, because this is the measured number, you should round to significant figures. So this one, I would round to 50. This one, I would round to 6 because I have 100. I didn't put 100 point, like exactly. I just said 100. So I would say that that's 6. There's one significant figure in 100, one significant figure in 3. So the bottom ones, you don't even have to use the periodic table. You just have to know how to put Avogadro's number in your calculator. So if you have your calculator, pull it out. Anybody not have a calculator? Because I brought them just to make sure. All right. So this one, so if I have 3 moles of CH4, how many molecules is that? If I want to go from moles to molecules or molecules to moles, it's just a matter of making sure you put it in your periodic table, in the calculator correctly. I know there is 6.02 times 10 to the 23rd molecules per 1 mole. So I can use this as a unit conversion. So I can put it on the bottom. I could flip this depending on how I want to use it. Just like I can use grams to moles as a unit conversion, just to change from one unit to another. So if I have 3 moles times the line, what unit goes on the bottom? Moles. So molecules goes here. And this is a given number, 6.02 times 10 to the 23rd. So you can just put it on your card for this next test. You don't have to memorize it. But here's how I want you to put it in your calculator. Do 3 times, put 6.02 EE, find the EE button, and then hit 23. And equals. So it would be, hold on, it should be 1.806 times 10 to the 24th.
You said the EE button?
Yeah, that one. See that? Yeah, exactly. Did you get it? 6.02.
If not, I have my graphing calculator.
I think it's this. Hit that. Yep. And then
Okay.
23rd.
Okay.
See it? Yep. see where the two little zeros come up? That's that button. That EE button then puts times 10 to the, and you'll see these two little zeros show up. That's the exponent. Then put 23. So the answer you get like on the little old-timey kind of calculators, you don't get a times 10 to the. It just puts the little number smaller and up in the corner, but it should be a positive number, and you should have gotten 1.06 times 10 to the 24th. Yours would say 1.06 and then a little 24 above, but that's what that means, okay?
So is that how we would write the answer?
Yeah, so that one, if we had to round, we would end up rounding it to 2.
Okay.
Because it's 3. So it'd be 2 times 10 to the 24th. So try this one. Again, you're still just using Avogadro's number in a mole as being your unit conversion. But in this one, 3.1 times 10 to the 21st molecules times in your line. In this one, the unit on the bottom would be molecules. The unit on top, the answer you want. It's just a single step. So you don't have to do like multiple ones with it, just a single step. See that molecules and molecules cancel. So this one you got to put 2 exponents in before you're going to get the right answer. Uh-oh. So 1.3 EE21 divided by 6.02 EE23. What'd you get?
A big number.
Big number?
Yep.
Like?
2.1594684.
Oh.
To the 43rd.
To what? To the 43rd?
E43.
No. Divide by?
It's 2.6. I
Uh-huh.
mean 2.2 times 10 to the 43rd. And then 2.
Oh, so in this, on yours, then you're going to have to use some clear, you have to use a brackets.
Okay.
So 1.3 times 10 to the 21 bracket divided by,
I got like 0.00215.
yeah, that sounds normal. That's why I'm like, Back.
I'm just gonna bring my
It should be. See, now it puts that divided by.
Oh, because you have to backspace and then you space it.
Oh.
Yeah, I got it. Yeah, I got it. That's
Now,
the right.
now divided by.
Yeah, I got
and then
point
bracket.
0.00.
6.02.
0.002159.
Yeah, that's what I got.
Yeah.
And then down bracket.
Okay.
0.0021?
Yeah,
Yeah, okay. 0.0021 something. So let's see.
5947.
Did you finally get that one? Yeah, 21. So it'd really be 22 because it's 159. So 1.3 times 10 to the 21 divided by 6.02 times 10 to the 23. Yes? Okay. Did anybody not get it?
Yeah, I fixed it.
And if you have it where you're typing it all out, yeah, then like the other thing is you may have to put brackets, like on the graphing calculators, you may have to use brackets around those numbers. And in yours, did you get it?
So you don't even have to put
You get it out?
times 10.
Will you show her so that she knows?
You don't have to like put 10. That's what I was doing. 1.3 times 10 and then like
Yeah, if you use your EE button.
yeah,
Mhm.
the E button. Okay, I didn't.
So it actually like takes a little bit of the steps away. Did you get it okay? Yes? All right. So it actually takes some of the steps out using that EE button. That would actually be 2, because it was 0.002159, so we would round that to 0.0022. All right, so here's a couple other ones. I don't even know where this one is. Sarah's not. Logan Edwards is there. Were you in class or you're coming tonight? You're coming tonight to class? Okay. Chelsea's here. Trina's here. So just Sarah's the only one that's missing. So if you see moles and you see grams, then you know you need to know the formula mass. Okay, if it's moles and molecules, then you'll just use Avogadro's number. So in the first one, H2SO4, you want to make sure that you add up the masses of each of the atoms in the formula. So we have hydrogen weighs 1 and there's 2 of them. Sulfur weighs 32, so always just take the mass, just round to the nearest whole number is fine. Oxygen is 16 times 4, so that's 64. So you'll add 2 and 32 and 64, and that's where I got the 98 grams in 1 mole. So it's just the mass of each of the atoms in the formula. So to go from moles to grams, which unit from over there am I going to put on the bottom? Moles. So the unit you start with always goes on the bottom in the first step. And so there, the 98 goes on top. So that would be 147. We'd like round that to 150. 1.5 grams. 50 grams of H2SO4 is how many moles? So again, if you see grams and you see moles, you just need to know what the formula mass is. So we can still use this. It's the same molecule. So we get what unit on the bottom this time? Grams. Moles on the top. So here, moles gets the 1, grams gets the 98. So 50 divided by 98, 0.5. What goes past that? 0.5, isn't it? 5, 0.
1, 0, 2, 0, 4, 2.
Yeah, so there's a whole bunch of other things. But if that's 50, that's one significant figure. So I would just round that to 0.5. Okay? But if you see moles and you see molecules, now you don't even have to use the periodic table. Just use Avogadro's number. So 9.03 times 10 to the 23rd. So we just say 9.0. 1.5, two significant figures. Remember that you keep those exponents. The exponents don't get counted in as significant figures. It's the number in front that does.